Hi everyone. Thank you for giving me this opportunity and speak on my current work. So today I will speak on decoding quantum chaos through eigenstate correlations, and I will present some exact result based on this. So this is a joint work with Ratul and Sridhari, and it will soon appear on archive. So the kind of system that I will speak for next 10 minutes will be some locally interacting quantum chaotic system. So by locally interacting, I mean the Hamiltonian of the full system can be written as a sum of this kind of local terms. For example, I mean they are sum of this nearest neighbor interacting terms, and the eigenvalues and the eigenvectors of the unitary operator that I denote by this alpha and this theta alpha are the quasi-energies of the unitary operator. And by quantum chaotic system, I mean if one looks into the any spatiotemporal correlator using this kind of Hamiltonian, what one will find that at long time and they will decay, and these kind of operators will be statistically independent from each other. So in any quantum system, given the joint distribution of eigenstates and eigenvalues, basically you know everything about the quantum system. So, but the information encoded in this joint distribution is actually huge. And in many-body system, as you know, the dimension scales exponentially with the size of the lattice. So this question that we ask is, what are the minimal correlations between eigenstates and eigenvalues that can encode the local dynamics? In other words, we want to understand what are the universal features of the eigenstates of locally interacting quantum system that will separate it from non-local chaotic system as well as from integrable system. So before going into details, I just want to explain why this question is interesting and all. So like all other physicists, I am trying to do some spherical curve approximation here, and the simplest or the crudest approximation that one can make for eigenstates here are basically their Gaussian random vector within some fixed energy window. And though this approximation may look like it's very simple and all, but it can explain why in an isolated quantum system, even though the dynamics is unitary, the system thermalizes locally. That is the 2-point local autocorrelation function that will decay over time. Also, this Gaussian approximation explains why the eigenstates are volume law in nature. The better approximation one can make for the cow on the sphere will be adding some white and black patch. So like that for the eigenstates, which are chaotic in nature, we can make them, because they are eigenstate, the better approximation will be they are random vectors within some fixed energy window, but they also satisfy the orthonormalization condition. Once we introduce this extra constraint, then we can explain the higher point local autocorrelation function. And because we are explaining some locally interacting system, we expect that the theory is not Gaussian anymore. So the higher point correlators are no longer be decimated into 2-point correlators. And just using this extra constant, one can explain the k-point local autocorrelation functions. So we want to go beyond this approximation. So by beyond, I mean there are certain observables which cannot be explained by the earlier approximation. So these observables are like this k-point spatiotemporal correlators or the entanglement entropy. One common thing about these dynamical quantities are they are sensitive to the system being locally interacting. So that's why we want to understand what is the signature of locality on the eigenstates. That is like, adding some spatial structure on the sphere itself. So we want to identify what are the imprints of these local interactions in many-body eigenstates. The question naively may seem complicated because we know the eigenstates in a chaotic system are delocalized, they spread over the full Hilbert space. So how can we identify some local signature on it? It may sound like looking for a grain of gold in a vast sea. But there can be a certain approach by which we can identify signatures of local interactions in this delocalized chaotic eigenstates. So to identify this, what we do is we write the eigenstates in some tensor product basis. So this I can be thought of as some tensor product basis. For example, let's say some sigma x or sigma y or some sigma g basis. And what we do is basically we split the basis states into this x and its complement. So the eigenstates which were initially a vector, now we write the eigenstate as a matrix on this bipartite Hilbert space. So now I want to identify the correlations among the eigenstates. So identifying or calculating any correlate is basically constructing a scalar from a set of matrices. The simplest scalar that you can form for eigenstates is basically from two eigenstates. So given two eigenstates, one can find out what is the correlation in between them. And because these eigenstates are orthonormal in nature, the correlator will give just delta alpha beta. So this is a trivial one that we know already. The simplest non-trivial scalar that we can define in this kind of system are from four eigenstates. That is, given four eigenstates, you can take the trace accordingly and define a scalar from them. And this obviously, because this is a trace, the scalar, this is basis invariant. But to make this scalar gauge invariant, we take the product of this eigenstate correlation to another eigenstate correlator which is defined at some y. So this correlation defined at here, we can consider another eigenstate correlator which is defined at some other point y. And we take some energy window from which we pick four eigenstates. So the eigenstate correlator that we are defining here is basically given four eigenstates. We can define the eigenstate correlation like this. And one can also look into what is the structure in the time domain. So in general, there are four such eigenstate correlators one can define, but they are related due to the symmetry from the bipartisan. So there are two independent, this f tilde of xy of omega and this f tilde of x bar y of omega. So by doing this approach, we expect that there may be some information in these eigenstate correlations about the local interactions. But is it so? So what happens that the kind of dynamical quantities which are sensitive to local interactions, like the 2-point spatiotemporal correlators or the out-of-time order correlators, those are different authors of this eigenstate correlations. So the 2-point correlation, that is basically this this kind of correlation when average over all kind of operator, it turns out to be just a correlation between x and y, and where the f function is defined above. And the out of time order correlator can also be written in terms of this eigenstate correlation. Just not local correlators, even the entanglement entropy, which is which can also be written in terms of this eigenstate correlator. I mean, here I looked into the purity, which is basically related to the second Renai entropy. That can also be written as eigenstate correlator in between x bar and y of the system. So depending on the interest of the dynamical quantity, whether it is local or non-local, we have to choose the system accordingly. If it is local, then x will be consist of just one spin. If it is non-local, something like the entanglement entropy, then we will consider x as some macroscopically large subpart of the system. Now, since we understand that the eigenstate correlator can explain this dynamical quantities which are sensitive to local interaction, whether we can calculate these eigenstate correlations exactly. It turns out that there exists a class of systems for which we can calculate this eigenstate correlation exactly. So these are known as these dual unitary circuits. So basically, I have some Floquet operator which I denote by this UF, which is basically a tensor product of local unitaries, and I apply this UF periodically t times to get the full unitary. And these local unitaries are basically some hard random blocks. So they satisfy the usual unitary property, that is when I sum over the indices along the time direction, that is the u dagger equal to identity by these two vertical lines with circles. I mean, they represent just the delta function of the identity operator. And this is basically u dagger u. By dual unitary I mean they are not only unitary in the time direction, they are also unitary in the spatial direction. So basically, if I contact the indices along the spatial direction, that also gives a delta function. That's the identity operator. So once we impose these rules on the full unitary circuits, one can explain the operator entanglement entropy that I defined in the earlier slide, also the 2-point correlator, the higher point correlators exactly. So what happens that for entanglement entropy in this kind of dual unitary circuits, one can calculate exactly, and one can find that there is a light cone which goes to this volume law at a long time. So since we know the analytical expression for the entanglement entropy, we can comment on this eigenstate correlation. And the eigenstate correlator at small omega, or that is the large time regime, has this following structure. It has this sine omega over omega like structure. One can also comment on the 2-point correlators, because we know the 2-point correlator exactly for this kind of dual integral circuits. We know the eigenstate correlation responsible for this exactly. We can also know this out of time order correlators. So in this kind of dual integral circuits, out of time order correlator has a light cone like structure. That is, within the light cone it decays exponentially and goes to 0. Along the light cone it goes to some constant value, and outside the light cone it's just order 1. I mean, it's just 1, sorry. It's just 1. And it also gives the eigenstate correlation as sine omega over omega like structure at small omega. So just 1 minute. So coming back to the main result of this work is basically adding some spatial pattern on the sphere itself. Without the constant from locality, we can always write this joint distribution of eigenstates, eigenvalues I mean, this joint function is separable without the constant of locality. But when we impose this constant from locality, this is no longer separable, and this kind of eigenstate correlations can explain this explain dynamical quantities which are sensitive to local interactions, like dynamical k-point correlators or the entanglement entropy. So there will be a talk by Ratul in the afternoon, after lunch, where he will explain this imprints of local interaction or eigenstates of integrable models. Thank you.
Thank you, Bikram, for the nice talk. We are now open for questions.
In your dual unitary model, did you have you mentioned that it was Haar random? Could you just clarify that point? Because I thought
no, no. Okay, then the blocks are not Haar random, sorry.
Exactly, because so you can have models without random, like the Kicktising model.
And this individual blocks satisfy these two properties.
Right. So in your particular model, you're looking at a clean model, right?
Yeah.
Perfect. Thanks.
More questions? Questions from online participants? Okay. If not, let's move on to the next speaker. Let's thank Bikram again, and